Okay, it's time to go ahead and begin. So today, the main topic is decoders. And after today's lecture and activity, you'll be able to finish lab 3. Lab 3 has an RCA that you the thing that you did in lab 2. And it has the MUX that we talked about last time. Now, how many people were able to simulate their MUX successfully? You raise your hands. Okay, not quite as well as my earlier section, but so yeah, if you didn't get a successfully simulated MUX, that's where you would start today after the lecture and activity. But if you have a good MUX, then the next step would be to design and test the decoder. Okay, and like I said, we're going to talk about decoders, and I'm going to start you with the code that you need in order to model the decoder in lab 3 with System Verilog. And then you'll have to connect the modules all together. So you'll need a file, it's the same format as what the RCA is. Okay, remember the RCA connected the half adder and full adders into an adding circuit. Well, the structural model, your top module this time will connect 3 modules together to make a circuit that adds 2 binary numbers, 2 4-bit binary numbers, and then we'll display the result as a hex if the result is 15 or less, and won't display the result. In fact, we'll have blank displays if the result is greater than. Okay, so anyway, that's sort of the game plan today. Oh, also, I just wanted to remind people, this is in the syllabus, it's on Canvas. I haven't changed anything. It's just I want to give you a heads up that the midterm is on Halloween, which is 2 weeks from today. If you go on Canvas and you go to modules and you click on the meeting for the midterm, you'll see that I have the topics along with my testing policy, so you can look at that, ahead of time if you want to. I will bring you a hard copy of the topics for the midterm and also, my testing policy next week. And I'll make some more comments, about the midterm at that time. Okay, but I just wanted to, put it out there that, it's a couple of weeks away. You definitely don't want to wait till the night before to start studying and say, oh, I didn't know this topic was going to be in there. What's this? Look ahead of time. That way, if there's something, you're not sure about, you have plenty of time to.
The midterm is from 8 to.
Oh, yeah, I got to update that. That was from you. Sorry, thank you. Yeah, I didn't want people showing the fear dates. Yeah, this would be from 12 to 1:40 because it's a 90-minute test. So, I don't think everyone's going to need 90 minutes, but you'll have. Yeah, thank you for putting that
up lab after that, or is it just guys?
Yeah, there's there'll be a short lecture.
Okay.
Yeah. I will probably not have a lab due the next Wednesday. I'll probably delay it. Yeah, but I'll let you know next week when we get closer. But yeah, I realize after a test, you probably, and then, a short lecture afterwards, you're probably not going to want to do a lab. Probably be burnt by that time. But anyway, I'll talk more about that. Like I said, my purpose today of even mentioning it is just, to kind of give you a heads up. So again, you can start preparing in a timely manner. Okay. All right. So like I said, the main topic today, decoders. But before we start discussing decoders, there's this BCD binary coded decimal that I wanted to go over. And before we go over binary coded decimal, what it is and what its purpose is, I just want to review something we talked about on the first day when we were talking about number bases and number base conversion. And that's converting from hex to binary and binary to hex without going through base 10. Okay, the reason I want to review this is because I have found in the past that if I don't review this and I go right to BCD, some students get confused because they start confusing it with this, and I just want to have them sort of like on the board at the same time, so I can talk about the differences. So anyway, let's talk about hex to binary, binary to hex, without going through base 10. So if I have a base 16 number like this, remember, one way to show a base is to put a subscript, right? So this is 1459 in base 16. So how can I go from base 16 to base 2 without doing base 10? Right, each hex character would be a 4-bit binary, right? So what would I write for this 9? It's 4-bit binary for 9. 1 0 0 1. Okay, what would I write for 5? Somebody on this side of the room. What's a 5? 4-bit? 0 1 0 1. Okay, 4 and 4-bit binary. And then what would you do with this 1 here? I mean, you could write 0 0 0 1, but you know, zeros to the left, isn't going to change anything, right? So I could just put a 1 there, but it would not be incorrect to do this. It's just, that's kind of a waste. Okay, but the key point is for each hex character, I'm writing the 4-bit binary equivalent, right? So that's how I can go right from base 16 to base 2. How about from base 2 to base 16? Go in the other direction. What do you do? This in reverse, right? And you start with the least significant bit, right? You just group in 4s. Again, here you could put some imaginary zeros. And we don't change the value with those zeros. Okay, so what would I write for this 4-bit group? 3. What would I write here? What's 1 0 1 1 in binary? What's that in base 10? 11, 11 in base 16 is. What would I write here? And why is it a group of 4? Like, what's the relationship where we group in 4 instead of some other number? There's 2 to the 4 is 16. So that's why this works. That's why it's groups of 4. If you were going octal to binary directly, right? Octal being base 8, what would you group the bits in then? 3, right? That's 2 to the 3 is it. So, this is base conversion, right? Because, if I now figure out what this base 2 number is in base 10, right? I come up with some value. And then I take this base 16 number and convert it to base 10. Well, I would get the same 2 numbers. Okay? All right, well now, let's talk about something new, this BCD, which again stands for binary coded decimal. BCD, it's a subset of binary. Okay, it's only binary from 0 0 0, and it's also 4 bits. Okay, 0 0 0 through 1 0 0 1. Okay, so BCD is just a subset of binary. It just includes 0 all the way through 9. And we use BCD sometimes to represent a base 10 number. So now I'll take this 1459 as a base 10. And if I want to write this base 10 number as BCD, I just write each digit, right? Each base 10 character as a 4-bit binary group. So, I would write this 1 as 0 0 0 1. I'd write this 4 as 0 1 0 0. The 5 as 0 1 0 1. The 9 as 1 0 0 1. And then this is BCD. So I put subscript BCD. But you see the key difference here between what we just did up here and what I just did here is that this is not base conversion. We're not saying that 1459 base 10 is equal to this uh, in like a binary sense. We're just representing each base 10 digit as a 4-bit binary group. Okay, but it's not base converted. So, write in your notes, not base converted. Right, because 2 to the 4 does not equal 10. Right, so when you write a base 10 number using the 4-bit grouping, you're not doing base conversion. Okay, like if you do the binary for this, it's not going to equal 1459 base 10. It's going to equal what it did up here. Okay, so that's the key thing. Is once people learn about this BCD, they start confusing it with this, but they're two totally different things. One's base conversion, one's just representing a base 10 number with bits each digit. Now, I'll come back to this once we talk about a 7-segment display and also a 7-segment display decoder. I'll come back to this and explain the purpose, like why they have this. Okay, but any questions up to this point? Questions? Okay, so first thing with decoders is this definition. It's a very general definition that decoders just take signals and convert from one form to another. And in this class we talk about converters that are taking digital signals, so taking bits, you're converting those bits into one form or another. But you can have analog circuits that are decoded, not just digital. One example of a decoder, and this is the one that's in lab 3 that you're going to design and build in Verilog, is binary to hex. You can have a decoder where you input binary and you output hex. Okay, so it's converting binary to hex in hardware that does it. Also in CP233, and I put this diagram of the microprocessor that you build in CP233. I put one of these on each table. So if you take a look at that diagram, and you look in the upper right-hand corner, not quite the very upper, but near the upper right, you'll see CU, then DCDR. That stands for control unit decoders. Now above that is CU FSM. That stands for control unit finite state machine. You're going to learn about finite state machines in a couple of weeks. Okay, right around the time of the midterm, or right after the midterm, I think we start talking about FSMs. Okay, but if you take a look at this control unit decoder and you look on the left side where the inputs are, up in the left hand, the upper left of the left hand side of that control unit decoder, you'll see IR, and then in square brackets 30, and then there's IR in square brackets 14 to 12, and then a little further up, there's a 7-bit input. See the /7, and it goes to this IR 6 to 0. Well, IR stands for instruction register, and you're going to learn about what a register is in a few weeks. Instruction, as the name implies, is an instruction, for the microprocessor. You're going to learn in that class something called assembly language. Okay, and assembly language has the various instructions for the microprocessor, and then the numbers indicate the bits. I think I mentioned earlier that most of your data that's in this microprocessor is 32 bits. That's why you see a /32 on almost every line. So each instruction to this microprocessor is 32 bits long. So, 6 to 0, that's identifying 7 bits of the instruction, bits 6 through 0, 7 bits of the instruction. And then 14 to 12, that's 3 bits of the instruction. And then bit 30, that's a single bit of the instruction. So, some of the inputs going into that decoder are bits for the instruction of the instruction. And then if you look on the output side of the decoder, you'll see ALU fun, ALU source A, ALU source B, PC source, and RFWR select. Now, when you take the class, you're going to learn about, what all those acronyms mean. But for right now, can you tell me where else you see those outputs? Like where else in the diagram you see ALU fun, ALU source A, ALU source B, PC source, and RFWR select? Or if you look at the rest of this diagram, can you identify like where those outputs connect to? Like where else do you see a tag with ALU fun? Yeah, see here the ALU. How about ALU source A? Yeah, see the mux. How about ALU source B? Anybody looking at the diagram besides Avery? Down here, right? This mux here, it's also by the ALU. How about PC source? The mux over here by PC. How about the RFWR select? Where else do you see that? Yeah, the mux right above this thing labeled reg file. So you see the outputs of this decoder, they're all going to muxes. You'll learn in that class that this ALU is basically a big mux. Okay. Well, specifically though, which input of the mux are those outputs going to? Yeah, they're all going to the select input of the muxes. And what does the select input of a mux determine? What the output's going to be, right? It's going to choose which of the multiple inputs the output is going to be equal to, right? So you see, the reason why this is called a decoder is because this decoder is taking bits of an instruction, and then by controlling the muxes, right, through the select inputs, it's determining how the data flows through the circuitry so that the instruction actually occurs. Okay, so the decoder, it's taking in bits that an instruction and converting that into routing data, basically, and through controlling mux, through selecting. That's why it's called a control unit decoder, because it's controlling how the data flows. Okay. So, anyway, there's all kinds of different decoders. I mean, yeah. In theory, there's probably like an infinite number of decoders, right? Because whether it's a digital circuit, like we talked about in this class, or whether it's an analog circuit, like with op amps or something, it's a common thing, right? You're taking some signal, converting it into some other signal. Okay. Okay, next thing is, let's talk about how a 7-segment display works. This is part of lab 3. Where you're going to use the 7-segment displays that are on your Basis 3 board. Okay, you have 4 7-segment displays. Okay, so here's a picture that shows how we label the segments. Each segment is an LED. Okay, LED stands for light emitting diode. How many people know what a diode is? But you know what an LED is, right? An LED is just a diode that gives off light, right? Passes through it. Okay, so we call the top segment A, right? So segment A, and then it's B, C, D, E, F, and then the middle segment is G. Now, you can see over here, each segment has an input, but then over here, there's an input that's just labeled AN. Well, if you know what a diode is, can you guess what AN is short for? Anode, exactly. Right, one side of the diode is called an anode. What's the other side of the diode called? Cathode. You see, that's what these pins are for. These are cathodes. Okay, so now this diagram is like a more detailed version of the 7-segment display. Here I'm showing each segment as an LED. Okay, LEDs, they have the diode symbol, which is this arrow with the vertical line, along with two arrows that show that, it gives off light when current passes through. So here's the AN input, and then what kind of gate is this? Not gate, right? That's the inverter. I'll explain why that's there coming up. Okay, but before we go further, just a little bit of circuits. Again, if you haven't had circuits, don't worry about it. This isn't testable, but for people that have had circuits, at the very least, it will tie in, what you've learned in your circuits this class. So you probably learned this during the first week of circuits 1. If you have a resistor and the current's flowing this direction, and in engineering classes, we always assume current is the flow of positive charges. Right? When you take a physics class, they might talk about electron flow, but electrical engineers and computer engineers, we always consider current as the movement of positive charges. So if this is positive charge flow, direction going this way, what's the polarity of the voltage across the resistor to get current positive charge to flow left to right? Like, where's the plus and minus going to go with the voltage? Yeah, here you have the plus on this side and the minus on that. Like, the positive charge flow flows from the higher end voltage to the lower end voltage when it goes through a resistor. Right? And we call the voltage across a resistor, we call it a voltage what? Voltage what? Well, you can have multiple resistors and have a voltage divider. That's a type of circuit. But there's voltage rises and voltage drops. You get a what across a resistor? A voltage drop. And when you have a voltage drop, is energy being absorbed or supplied? Absorbed, right? Because resistor can't supply energy, right? They can only absorb energy and they dissipate it as heat. Okay, well, the reason why I bring this up is because a diode or an LED, it also can only absorb power. Okay, diodes can't supply power. And positive charge flow through a diode or LED is always anode to cathode. And to get positive charge flow to flow anode to cathode, you got to have a higher voltage on the anode side than what you have on the cathode side. And then the other thing about diodes, and this is the difference between a diode and a resistor, is that, with the resistor, if I reverse the voltage, right, reverse the polarity of the voltage, the current's going to flow the other way. But with the diode, if I reverse the voltage, I put the higher end of the voltage difference on the cathode and the lower end of the voltage difference on the anode. Well, the way diodes are constructed, they won't allow current to flow cathode to anode. Ideally, you'd have zero currents. You probably heard forward bias, reverse bias. Yeah, see, this is forward bias when current's flowing anode to cathode. Reverse bias is when you have the opposite, ideally no current. Okay? So in order for an LED to light, you have to have current flowing through it. And in order to have current flowing through it, you need a higher voltage on the anode compared to the cathode. Okay? Now, the 7-segment displays that are on your basis board, they're called common anode. A common anode 7-segment display. And the reason for that is because all these segments, all these LEDs, they're all connected together on their anode side. Right, so you see this node here that's connecting the anodes of all the segments. That's what's referred to as a common anode. Like I said before, these are your cathodes. And do you know what letter we use to indicate a cathode? Okay, why don't we use C? What's C for in circuits? A what? Oh, it's for that. Yeah, it's for the unit of charge. But what component is C for? Capacitor. But it's also for cooling, the unit. So these are your cathode. You need to charge. Okay. So in order for one of these LEDs to light, and remember, in a digital circuit like this, we only have two possible values, right? A 1 or a 0, where, a 0 represents 0 volts and a 1 represents, some plus amount of voltage, like 5 volts. Well, in order for an LED to light, we want this common anode to be a 1. Okay, because that would be some plus amount of voltage, say like plus 5 volts or plus 3.3 volts. And in order for a segment to light, what would I need on the cathode? If my anode's a 1, which again is like 5 volts, what would I want on a cathode in order to get that segment to light? Would I want a 0 or a 1? You'd want a 0, right? Because a 0 is like 0 volts. So you'd have, 5 volts on one side or 3.3 volts on one side, and you'd have 0 volts on the other, and current would flow, to cathode, and it would light. So if you put a 0, okay, you put a 0 on the cathode in the segment, that segment will light. If you put a 1, well, now you got equal voltage on both sides, right? You'd have 5 volts on the anode and 5 volts on the cathode. And if you have equal voltage on each side of something, what's the voltage across it? 0. And is any current going to flow if there's no potential difference? No. So you see, this would be, that segment would be off. Okay, so with a common anode, a 0 is going to light the segment, and a 1 is going to not light the segment. All right, well, now there's this NOT. And the reason why this NOT gate is there, and by the way, there's this handout on the table, and there's enough of these for everyone. And you can pick one of these. In fact, on the back side is something you need for the constraints file for lab 3. But on this side, this is a page out of the reference manual for the Basic 3 board. Now, if you look on Canvas, I posted the reference manual for the Basic 3. And everything you ever wanted to know about the Basic 3 is in that manual. Well, this just talks about the 7-segment display. It talks mostly about what I went over. But one other thing that's on that handout is that it explains that in between this common anode and the input to the 7-segment display, there's this NOT gate. And you might remember that back, I think it was the second meeting we had, I showed you electronic circuit for a NAND with a transistor with a couple of diodes and a resistor, or a couple of resistors. Well, you can make an inverter with one transistor. Okay, one transistor acting like a switch acts like a NOT gate. And the other property of a transistor, besides acting like a switch, is that it can provide current gain. Now you're going to learn about like how it does that and all that. You take your first 300 level electronics class. But you see, the purpose of this NOT gate, which is just a transistor, is to provide some current gain so that these segments will light up bright. If that NOT gate wasn't there, the segments would still light, but they'd be pretty thin. Okay, so this inverter, which is just a transistor, it provides some current gain, so we get brighter LEDs when they light. So if I need a 1 on this common anode, right, in order for this display to work, well, what does this AN pin have to be? What value? Yeah, it's got to be a 0. And so you got to put a 0 on this AN input in order to put a 1 on the common anode node, so that what we just discussed will work. Okay. All right. So, any questions about this? I could have just, basically just showed you this and not even talked about any of this circuit stuff and just went into the truth table, and you could still do the lab. But I chose to spend some time on this, mainly because, most people have had some circuits, but even if you haven't had any circuits, again, don't worry, you're not going to be tested on this, but, I think it gives you a little better understanding than if I didn't talk about it at all. Okay, the things we've maybe seen more like magic. Okay, let's get gonna move the camera. So any questions as I move the camera? You have a question? Oh, okay. Yeah, just let me get this situated and I will answer that. Somebody messed with my camera over the weekend. Kind of. Oh, there it is. It's a little bit better. Let's see. All right, yeah, so. Well, let me ask. So everything to the right of this dot gate, you're good with? Okay, so. You see, we could take that dot gate out, just have a straight connection from this AN input right to the common anode. But if we did that and then made AN a 1, everything I talked about over here is still the same. However, the LEDs, when they're biased, so current flows through them, they wouldn't light very brightly. They'd be kind of dim. And that's because, you know, what this is connected to, it doesn't quite have enough like current capability. So putting the NOT gate there, which again is just this thing called a transistor. You know, you're going to learn all about transistors like in your first three. Well, are you EE or CPE? Yeah, EE's, you know, you take a trilogy of semiconductor classes like 306, 307, 308. 306 is when you learn like the basics of diodes and transistors and things like that. So, you know, when you take that class, you learn that there's two basic uses of a transistor. One is a switch, okay, electronic switch. The other is an amplifier. But even when you use a transistor as a switch, you can still get current gain from it. Now, you won't get the optimum like you will when you use it as an amplifier, but you can still get some current gain. So that's why we're putting it here, because the thing it's connected to doesn't have like enough oomph, if you will, enough current in the NOT gate. The transistor provides some oomph. It provides some more current so that when a segment lights, it lights up brighter.
The allows more room to flow through each of them. Like,
Right. For segments that are biased such that current will flow through, with the NOT gate there's a higher level of current, so it's brighter. Because the more current you put through an LED, the brighter it gets. Okay. That help? Yeah. Any other questions? Okay, so the next thing we're going to do is come up with a truth table for a hex to 7-segment decoder. Okay, and this is one of the modules that you're going to need for lab 3. Okay, so you're going to design this and test it just like you did the MUX, just like you did the RCA. Okay, so the input to this decoder module is 4 bits. See, the 4-bit sum output of the RCA is connecting up to this BIN, which stands for binary input of this decoder. It's this bin underscore X. This is the decoder. You know, you could call it 7-segment display decoder if you wanted to, okay? But I chose to call it that. So since this binary you know, decoder input is 4 bits, how many rows am I going to have in my truth table? How many? 16, right? 2 to the 4, 16. So 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0. Then there's a number of times now on the left, right? 1, 1, 1, 0, oops, that's not right, 1, 1, 1. Right, so did I make a mistake here? Let's 0, well, 2, 4, 6, 8. 2, 4, 6, 8, 10, 12, 14, 16, 0, 1, 3, 4, 5, 6, 7, 8, 11, 12, 13. Yeah, it's always good to double check, right? Because you can easily mess up a 0, 1 or something like that. Okay, so this is what's going into this decoder model. Now, the next column, I'm going to show which segments have to be lit to show this binary as a hex character. So if I've got 0, right, going into my decoder, I would want to show a 0 on this display, which means I would need the A segment lit, the B, the C, the D, the E, the F, but I would not want the middle segment to be lit, right? And if I just light up the perimeter LED, that will show a 0. Okay, if I've got a binary 1 going in, well, I would just want B and C segment, right? That would show a 1. If I got a binary 2, I would want these segments still. Right, and you see I would do that for all the combinations for a 3. And you just keep filling on. I'll let you, unless there's one you want me to do. But once we get to a binary 10, 1, 0, 1, 0, what do I want to light up since this is a binary to hex converter? Yeah, you want A because 10 in hex is A, right? So here you'd want, capital A. Right, so you light up everything except B to get a capital A. How about for an 11? What would I want to light up for an 11? What's 11 in hex? A B. Would you display a capital B or a lowercase b? Yeah, why lower? What's the problem with displaying an uppercase B? It's gonna look like an 8, right? So yeah, for B you want to do a lower. Okay, but then uppercase C. See a problem with uppercase D? What's the problem with that? Looks like a 0. So you want a lowercase for that. All right, then you have a capital E, capital F. Right, so everybody see what I'm doing here, right? I'm just figuring out what segments have to light for each of the hex characters based on the corresponding binary. Okay, well now, this next column of the truth table, we're gonna figure out, well, what cathode, these are the cathode inputs. E, F, E, D, C, B, A, and those are the cathode inputs here. So now we got to figure out, well, what do the value of those cathode input have to be in order to get these segments to light? So what binary, right, it's going to be 7 bits. What 7 bits would you put here to get a 0 to light up? Which ones? Say. So these 6, you would want a what? What value? 0. And then what would you do with G? Yeah, make it a 1. Yeah, so it'd be 1, 0, 0, 0, 0, 0, 0. And we see we made these 6 cathode 0 because that's going to light the segment, right? The segments we want lit, we make the cathode 0. The segment we don't want lit, we make it a 1. Right? So the only one we make a 1 is G because that's the one we don't want to light up. We want to light up all the other 6. Okay, how about to get a 1, which is B and C lit, what would you put here? Yeah, exactly. The only two that would be 0 is B and C, right? Everything else would be a 1. Right? That's only going to light segments B and C. Do another one, or can you get the rest of the table? You want to do a 2? How would you get a 2 to light up? Okay, say it slow down. Go ahead. Does everybody agree? Because which ones wouldn't light up? Let's see, C would not light up. And F would not light up, right? So that would give us a 2, right? Okay, so do you want me to do more, or could you do the rest of it? Right, because the rest of it is just the same thought process, right? You're just putting 0s for the segments that you want lit, putting 1s for the segments that you don't want to light. Okay, so the next column, even though it's not absolutely necessary, it's a good column to have. And that's showing these 7 bits, right? The 7 cathode bits, showing it as hex instead of binary. So how can I quickly go from these 7 bits, right? The 7-bit binary to hex. I mean, we did it earlier today. What did we do to go directly from binary to hex? Groups of 4, starting with the least significant bit, right? So I do this. Right? I write those 4 as a hex character. Now, there's only 3 here, but again, you can just imagine you put a 0 to the left, right? You're not changing anything. So what would you write for a hex in this? $40, right? 40 hex. Right? Because 0 and then no 1, no 2, we got a 4. So 40 hex. How about this one here? Somebody on this side of the room. Or in the middle. What? How would you write that in hex? $79. Right? 1001, that's 9, right? And then 317. We'll do one more. Do this one. 24. Okay. So this is, some review from like the first day of class. Now, this also shows again why hexadecimal is a popular base in digital. Because instead of saying 1000000, I can just say 40 hex. Instead of saying 1111001, I can say 79 hex. Okay, so hexadecimal, it's sort of like a shorthand for binary. And when you take CP233, again, your data is going to be 32 bits. Instead of saying some data with 32 zeros and ones, you can say it in 8 hex characters. So again, it's shorthand. All right, so for lab 3, for lab 3, provided that you have your MUX all simulated and working correctly, because if you don't have your MUX simulated and working correctly, that's where you want to start, okay? But if you have your MUX simulating correctly, today, once the activity is over, the lecture and activity, this is where you would start. You would want to fill out this truth table for all 16 rows. Okay, because you're going to need this when you model your decoder. Okay? So before we move on, any questions up to this point? Does everybody feel confident they can fill out this table? Okay, good. All right, so let's go ahead now and talk about how you're going to model your decoder in System Verilog. So just like any module, you have module in the name. Now, I'm pretty sure, I'm not 100% positive, but I'm pretty sure that Vivado does not like it when you start a file name with a number So that's why I wrote out 7 instead of putting a 7, but Vivado, I'm pretty sure will give you errors if you start a file name with a number. Okay, like I said, I'm not 100% sure, but I'm almost 100% sure. Okay, then you would declare your inputs and outputs, just like before. You're gonna see that just like when you did the if statement for the MUX last week, that for this decoder, we're gonna use a case statement. And when you use a case statement, it also has to go within an always comb block. And last time, you know how we talked about that any output within an always comb, you got to write output logic when you declare it. Well, same thing here. So see, we're going to have this output seg that's going to be within an always comb. You're going to see that coming up. So because of that, when we define, put it right here, when we define output seg, we're going to have to do output. And then logic, and then seg is 7 bits, so it's going to be 6 to 0. Okay, you're also going to have to define, input bit or input bin, but that you know how to do that, so you can fill that in. Okay, so after you declare your inputs and outputs, then comes the always comb, always underscore comb. Then you need a begin, okay, to begin that. Okay, now comes the case statement. So case, and then a case statement, it has parentheses, and what goes inside the parentheses is what's called a sensitivity list. And for us, it's going to be whatever we name the input. So I name this input bin. And the reason I put that within the parentheses and make it part of the sensitivity list because whatever you put as your sensitivity list, when that changes, that's when the case statement gets evaluated. So we want this case statement to be evaluated every time our sum output of our RCA changes, right? Because when that changes, this input's going to change, right? Because they're connected directly together. Okay. All right. Then the next thing in the case statement comes the option. So you'll list your options just with base 10 numbers. So you put 0, then colon, and then this is where we use our truth table. Now we're going to assign the seg output, the binary that we figured out for each of our hex characters. So when we have a 0 going into our decoder, we want the display to show a 0, and it will show a 0 provided that the seg output is equal to these bit values. So you see, I would put seg equal to 7 tick mark B, then I just copy what I have in my truth table: 1 0 0 0 0 0 0 with these semicolons. Oh, question.
Is there a way in System Verilog to display X values?
Yes. Yeah. Instead of doing 7 tick mark B and then the bits like this, you can do 7 tick mark H and then put 40.
So you're still going to set.
Yeah. Yeah, I know. You would think it would be 2, right? There's 2 characters, but yeah, that's what I thought when I first did it. But yeah, it was showing error. You have to put the same number as what bits would be. Like in CP233, you'll use case statements where the output is equal to 32 bits. And a lot of times, well, more than a lot of times, you'll always, because you don't want to do 32 bits, right? Right. It's easy to make a mistake. So yeah, there you would do like 32 tick mark H, and you put like 8 hex characters. Yeah. Yeah, I know. I got tripped up on that the first time because it seems like you put a 2. Yeah. Okay, and then you basically are just translating your truth table over to the case statement. So if the bin is a 1, then you want seg to equal 7 tick mark B, and you want it to be 1 1 1 1 0 0. Okay, and you would keep doing this all the way down to 15. Okay. And then with the case statement, you always have to end it with a default. So after your last option, which is here 15, you would have default. It's default and colon. And then you would just put say, and you can make your default equal to whatever you want. I made it equal to all ones. The default is there in case, like there's a situation that for some reason, the code gets hung up. I mean, an example in practice of why you would want to default is like, if you had some electronic, some digital system that was in a harsh environment, like maybe it was on a satellite and the satellite got bombarded with solar flares or something. There's a bunch of photons that changed a bunch of bits all at once. Well, then you could get in a situation where you basically got hung up, like it was in between choices because several bits changed, roughly at the same time, although nothing happens really at the same time, right? Like one bit might change a nanosecond before another one, but it might be enough where it causes the causes like an ambiguous situation. And having the default will keep it from getting hung up, like an infinite loop or something like that. So you always want to have a default. The other reason you always want a default is because if you omit a default in a case statement, it's going to create a latch. Okay, you know that word we've been using, latch? I told you, if you get an error where it has the word latch, treat it, or if you get a warning with the word latch, treat it like an error. You got to get rid of it. Okay, and that's because, and you'll learn more about this in a couple of weeks, but a latch is like the main circuitry of memory. So when you have a latch, you have memory, and that's additional circuitry. And remember, this COMB, you remember what it stands for? What word it is? Combination. Very good. And you remember the key characteristic of a combinational logic circuit, all the circuits we've been looking at thus far this quarter? There's no memory. So this decoder is combinational, no memory, but if you forget the default, Novado is going to put memory in that decoder, and that's additional circuitry. And in this class, it would probably still work. Like if you have unintended latches in this class, because the designs are not that complicated, especially compared to something like this, this is a challenge. Believe me, CP233, that's a challenging class. Well, even though having unintended latches, you may get away with it in this class where your design will still work. In CP233, if you have unintended latches in that microprocessor, it's not going to work. Guaranteed it's not going to work, right? Because timing is very critical for that, well, for parts of it anyway, of that microprocessor. Timing's not a concern really in this class. Now, it may be for your team project, depending on what you decide to do for your team project. For your team project, if you have an unintended latch, it may, be the reason why the project doesn't work. Okay, but let's finish this. So you need to follow. Oh, one other thing before we finish this, because I forgot to mention this last class when we were talking about the if statement. Remember when we talked about the if statement, you got to have an if. The else if is else ifs. The else ifs are kind of like a wild card, right? Because you can have as many as you want, or you could have zero. Okay. Well, also the thing I didn't tell you last time is that if you want to avoid a latch with an if statement, you got to end it with an else. Like if you don't have an else in an if statement, it's going to create a latch. Okay, now you'll see when we get to memory in a couple of weeks that when we do want memory, that when we do want a latch, that's the most common way we'll do it, is that we'll use an if statement where we don't have an else. Okay. All right, but to finish this, after the default, you would end the case. So you have end case. Right, that ends the case, and then you want to end this begin, which is the always home block, so you have an end for this begin, and then you end module. Okay, so, for lab 3, where you start when you want to build your decoder is you start by filling out this truth table. Once you have the truth table all filled out, now to model the decoder in System Verilog, you just got to finish this case statement, right? I kind of, gave you the format. Now you just got to fill in the gaps. Right, so is everybody confident that they could do this, the truth table in the case statement? Okay, now we're a little past the top of the hour. I probably have about another 15 minutes or so, 15 to 20. Do you want to take a little break first, or do you want me to keep going? Want to take a break? Yeah, let's take a 5-minute break till 10 past, and then I think I'll be able to finish by 1:30, and then you can do the activity and start working on lab. Yes, sir. Well, oh, you did this. Did you use a case statement? Or did you... Oh, okay. So, I mean, did you just? I didn't talk about case statements. Oh my God. Okay, well that's fine. Okay, well. All right. Well, all the sim files, every science specific in this class, it's the same format as the previous. What's going to be different is, what your inputs are, and the name of the file that you're testing, and then you test this to different. But see, what I do is once I have that's good, I'll just copy and paste the previous sim file into my new project, and I just edit it. That way, I put at least the format. Because I have found that people that tend to editing every time that you have, they tend to make mistakes. Oh, you did? Okay, good. All the simple, you're gonna be the same, but the only thing that's different is, you have to change the color of the, you're right. Yeah, so yeah, this thin file is the way they're going to be the inputs right here. Okay. No, the comparator is a different. Well, it's also this class. Like I expect you to know how. I mean, all the comparator does is takes two inputs, and that's the main applies. It compares, with A is greater. Yeah, the only reason I chose the comparator is because even though it's not in any of the labs, it is something that a lot of the team project with. But then it was just an example of an instant. In fact, that if statement for the comparator is much more complex than because remember the month is just choosing between two inputs, right? That, the mux has multiple. Mux always has one. And because we have two inputs, and select, which is going to determine one of these. This is connected, so it only has to be a single thing, right? Because when this is zero, all the things happens. Okay. If not, this thing comes up. So your if statement's going to be very simple, because if like this, outputting this, else outputting this. Yeah, you don't even need it all together. We have two on the. Okay, I think it's time. Okay, so let's go ahead and pick up again. Like I said, I think we'll be done by about 1:30. Okay, so this is the lab 3 circuit. Okay, and the purpose of this circuit is that it's going to add A and B together, and then it displays the result on the furthest to the right 7-segment display if the result is less than or equal to 15. If the result's greater than 15, it does not display the result, and all the 7-segment displays are off. Okay, they're blank or off. Okay, so you got an RCA from lab 2. So, like I said, you just go. All you got to do is add your RCA design source and your full adder and half adder design sources from lab 2, right? Just bring them over. You don't have to simulate them again. So you don't need the test bench file because you already, assuming your lab 2 worked, your RCA is good, right? You just bring them over into your new project. Okay, now if you simulated your MUX correctly after last class, you'll already have a MUX design source and you'll already have a MUX test bench. Okay, so if you're not at this point, you start with the MUX. But if you have all of this, then where you start today is you want to do a design source for this decoder. You can call it bin_x, or you can call it decoder, whatever you want. And you'll need a SIM file for this also. How many test cases are you going to need for the decoder? 16, right? You want to show that your decoder gives this truth table. Oh, one thing I want to mention, because this has come up with some emails that I've received, and also I noticed on some of the grading that the graders have done that they've made this comment. Now, I have 3 sections, so I don't know if the comments were made in this section or one of the other ones, but I'll mention it anyway because you may run into it. And that's, I think a number of people missed that in my intro to Vivado video, I show in that video that you can change the base of the waveforms in your timing diagram. Like I think it defaults to binary or maybe even defaults to base 10, but you can change it to, like say it defaults to base 10, you can change it to binary, you can change it to hex. Like up in the upper right-hand corner of the screen when you're looking at the timing diagram, there's a gear symbol. And if you click the gear symbol, you'll see there's an option where you can change the base. Okay, so I mentioned that because when you go to verify that your decoder is working, if you're looking at these 16 test cases on your timing diagram, if you change the base to hex, then all you have to do is look for these here, as opposed to, looking at the binary bits and making sure they're right. Okay, so it might be more convenient just to put it in hex. Okay, so you're gonna need these design sources, these test benches. You'll also need a design source that's gonna connect these all together. Right, just like the RCA connected the full adders and the half adder together to make the adding circuit, the RCA. Well, you're going to need a structural model, a top module that makes the connections between these modules. Maybe you call it. Let's see, what did I call mine? I think I just called it adder _ hex converter, same like HC maybe. So you'll need a design source that connects these modules together along with a SIM file. Okay, and I'll talk about the test cases that you're gonna need for the overall, coming up. Okay, but let's look at this diagram and let's put in the inputs and the outputs for our high-level black box diagram for this adder hex converter. So how many main inputs do I have? How many? 2. A and B, right? The 2 4-bit numbers that are going to get added. Now, how many main outputs do I have? How many? Thought I heard it. Who said it? 2, right? What 2 are the main outputs? Yeah, seg and AN. The seg is 7 bits. AN is 4. Okay, so remember, AN, that's the anode input. AN determines whether a segment's going to light at all. And then the seg, that's the cathode bits, right? That determines which segments light. Okay, so that's your high-level black box diagram. So remember, the high-level black box diagram, that gives you the inputs and the outputs that you have to declare in your overall, right, your structural design, right? So that's going to be the inputs and outputs that you declare these files here.
Why is AN 4-bit?
The reason why AN is 4 bits is because there's 4 7-segment displays on your basis board. So each display has an AN. So for example, if it's the furthest to the right, well, when you're looking at the basis board, if the switches are on the bottom, the furthest to the right 7-segment display, that's your 0th display. So you'd have like AN0, that would be the bit for that display. Then you'd have an AN1 for the 7-segment display that's just to the left of that one furthest right. Then you have AN2, AN3. Okay, likewise, you have like seg0, seg1, seg2, and all that. Yeah, I'll show you in the constraints when we get to that part. Okay, but getting back to this diagram here, let's talk about how this works. Well, actually, before we talk about how this works, I intentionally left out 2 things from this diagram. You know what I left out? Well, the half adder and the full adder, they're contained within the RCA. So, that's why, when you bring over the RCA, you do have to bring over your full adder and half adder because of that. Yeah, exactly. I left out the internal signals. Remember in the RCA, when you were connecting the adders together, anytime you had a lower level to lower level connection, you had to define an internal signal. We use T1, T2, and T3. Again, you can use any label. In fact, I would try to be more descriptive, like, for example, the internal signal that connect this carry out to this select, maybe you could name it COSL or SEL, CO_SEL. And maybe this would be internal signal sum_bin. And again, if you get in the habit of being more descriptive with your names, it's going to help you, especially in CP233. All right, so you all know what the RCA does, right? So it's going to add these 2 4-bit binary numbers, give you the 4-bit sum here, give you a carry out bit here, right? That's lab 2. We just went over the decoder, right? The decoder is going to take whatever binary is at its input and then show that binary as a hex character on the 7-segment display. Okay, but what is this mux doing? Notice that the output of the mux goes to the AN bits that we just talked about, that, there's an AN bit that goes to each 7-segment display, and the AN bit determines whether the display will light at all. And then look where the select goes. The select goes to the carry out. And what's the significance of the carry out? Like, what can we say about the result? The carry out is 0. What's that?
that input. Oh, if it's zero,
if it's zero.
then it will display number zero.
Right, because if the carryout is zero, we know our result is less than or equal to 15. Right, but if the carryout is greater than 15, what is it going to equal? Carryout is going to be equal to what if the result is greater than 15? Is it going to be a 1, right? Because when the carryout is a 1, that's equivalent to 16, right? So if you had 1 and all your sum bits were 0, that would be a result of 16. Right? So if your carryout is 1, you know your result's greater than 15, and that's when we want the result not to be displayed, right? We want all the displays to be off. Okay. Well, do you see why input 0, the mux has this data 1, 1, 1, 0, and why this input in the mux has all ones? To see this bit right here, that's the AN to the 0 bit. This is AN to the first bit. This is AN to the second bit. And this is AN to the third. So you see, this is the ANO bit for the furthest to the right display. This is the ANO bit for the next display to the left. This is the ANO bit that's 2 displays over from the furthest to the right, and then this is the ANO bit for the display that's 3 over from the display that's furthest to the right. So can you see what's going to happen here? Because what's going to happen when my carryout is equal to a 1, meaning I have a result greater than 15? What's going to be at the output of this mux? What's a 1? It's going to be all 1s, and all 1s is going to shut off all the displays, right? Because if AN's a 1, that's going to make the output of this inverter a 0. That's going to put all zeros on the common anode. And if you have 0 on the anode, there's no way a segment can light. Okay, and then if our result is 15 or less, we'll have a selective 0, and that's going to put this data 1, 1, 1, 0 at the output of the mux, which is going to be our AN. So that will turn off all the displays except for the furthest to the right. Therefore, the result of our addition, since it's less than 15 or less, it will show on our display. Okay, so you see how the mux is making this happen as far as when the result is shown and when it's not shown. Okay, this is very common use of a mux, is that you have a single output and you have multiple, multiple values that output can equal. And the mux determines which one of those inputs becomes the output. All right, so the next thing I want to talk about is how you do this, how you connect the inputs of the mux to this data. Okay. Now, one other thing, and again, I'm not 100% sure on this, but I'm pretty sure I don't think Vivado likes it when you name inputs a number. Like I wouldn't name this input 0 and this 1 like I've written on the diagram. I just did that for space reasons because I didn't want to actually spell out like 0 and 1. But when you actually do this, I would actually write 0 and 1 or use some other like letters for those inputs. But where you make this connection, these connections to the mux inputs to the data is in this file here, and you're making all the other connections. So in your structural model, connecting them all together, you would have, for example, let's say you call your mux file mux. Right, so you'd have file name, and then the next thing is the label. Maybe you call it mux 0. And you have parentheses, and then to make this connection, you would go .0, and then in parentheses, you would just put the data. Go 4 tick mark B 1 1 1 0. 4 connections. But this code here makes this connection between this input and this data. Okay. All right, so I think that should be enough You get your star in lab 3. Now, the test cases for lab 3, and they're on Canvas, but they're the same test cases as lab 2. Those same test cases as lab 2. So, you do those same 10 test cases that you tested out your RCA with additional, same test cases lab 2 with additional test cases, verify. Right, so you have to add additional test cases to verify that all the hex characters are displayed as they should be. So what I would recommend, because I think this is the best approach, so you don't, accidentally not have all the test cases or have a thorough test, is do the same 10 as lab 2, the same 10 additions, but then like set one of these inputs to 0. And then with the other input, just go 0, 1, 2, 3, 4, 5, 6, 7, all the way to 15, just to make sure that all the hex characters are appearing as they should. Okay, because sometimes it's very easy to like reverse a 1 and 0. And then when you look at what's being displayed, there's like a segment that's not right, and that happens quite a bit. Okay, so if you do the test cases that I just suggested, that would be 26 test cases, right? It would be 10 from lab 2, and then another 16 just to make sure all 16 characters are appearing. Some people, they try to do, they do the 10 from lab 2, and then they're like, okay, well, the lab 2 test cases showed these characters, so now I'm only going to do the ones that didn't show. But a lot of times when people do that, they miss 1 or 2. And remember, if your demo doesn't show that your design works 100%, you'll lose those points for the demo. Okay, again, it's got to work 100%. I talked about that on the first day. I've noticed some of the graders have been pretty lenient where they're allowing, people to resubmit, like if they miss a test case or if they, don't do the right ones. But that's going to change really soon. Okay, at this point, you should now know what test cases to use, right? You got to use the ones I provide. And you got to get in the habit of being meticulous and making sure that you don't miss stuff. Because again, when you take CP233, your microprocessor, that microprocessor, it's not going to work if any of these modules that you see here, if any of these are not working 100%, it's not going to work. All right, so again, I know it's harsh, but it's harsh for a reason. It's preparing you for the next class. Okay, last thing, and then you can get started, and that has to do with the activity. So everyone should have a handout that has the activity on it. It's a word problem. So if you want to take a look at it, I want to make a few comments about it. Does everybody have one? Don't have one. Anyone else need a handout? Okay, so from this word, anyone else? Everyone got one now? Okay, so this activity I think is a little bit more challenging maybe than previous activities, but judging from my 8 to 11 section, quite a few students liked it. They liked it. And I didn't coerce them to like it. They just came up to me and said, "Oh, this was pretty cool." So anyway, hopefully you'll like it too. So what I want you to do is to design a logic circuit, and you're only allowed to use an RCA, one MUX, and one logic gate. So one AND gate or OR gate or NOR gate or NAND gate. I mean, you got to figure out what gate it is. And you want to take those 3 components and make a circuit connect them up in such a way that it does the following, that it adds two binary bits, A and B, and outputs a single bit. Okay, a single bit output indicates whether the summation of A and B is even or odd. If the summation is greater than 15. The output a 1 if odd, and 0 if even. If the summation of A and B is 15 or less, the single bit output indicates whether the A input is divisible by 4. And the single output equal to 1 if A is divisible by 4, and 0 if A is not divisible by 4. Okay, so this problem here is what the person who designed this lab had to do. I didn't design this lab. It was either Dr. Benson or Dr. Neely. Might have been Dr. Hunt, but I think it was either Neely or Benson. They had to sit down, they had to think of it first. They had to say, oh, I want the students to do a circuit that will do this. Then they had to actually, come up with this diagram. Okay, so this problem, you're doing the same thought process as like an instructor would have to do to, develop this particular lab. Okay. Now, a big hint on how to do this is to write down all the combinations for the output of the RCA, right? Your RCA has a 4-bit sum and a 1-bit carry out. So you have a total of 5 bits, right? So the sum, when the carry out is 0, the sum is 0 to 15. Then when the carry out becomes a 1 and your sum is all zeros, that's 16. And then you can go from 16 to 31. Because 31 is when you have 5 bits all equal to 1. So what I would do is, I didn't write this all out. You can fill in the gaps, but I would actually just write out, like I've done here, 0 through 31. And then what you want to look at is you want to look to see if you can see patterns. Okay, like, since it's saying that the single bit output indicates whether the summation of A and B is even or odd, well, look at all the evens and look at all the odds and see if you can see a pattern. Okay. And then where it says, if the summation of A and B is 15 or less, the single bit output indicates whether the input A is divisible by 4. Well, look at all the binary that's divisible by 4. And for purposes of this activity, 0 is divisible by 4. Also, 0 is even. Okay. But write out all the binary, the ones that are divisible by 4. And again, look to see if you can see a pattern. Okay. Now, I'm going to run this activity just a little bit different than previous activities. I'm not going to put up my solution until I receive a submission from each table. Once I receive your submission, I'll check it off because everybody's here, right? I don't have anyone absent. Let's see, we got 2, 6, 10, 14, 18, 22, 26, 29. Yeah, everyone's here. So, I would give your group maybe like 15, 20 minutes, see if you can figure it out. Then hand in your best solution that you have after that time. And then once I have a submission from each table, and I'm just going to check it off and hand it back to you once you hand it to me, because like I said, I know everybody's here. So once I get a submission from each table, then I'll post my answer and you can compare it to mine. Now, this is the first time I'm running this activity. I haven't run this activity before, but I did run it from 8 to 11, and I had groups that matched my solution. I also had a group that had something slightly different, but it was still good. So there's not just one solution. Okay, there's more than one solution. Yeah, so like I said, I'm not going to post the solution until I have a submission from each table. And then after the activity, you should all start working on lab 3. Okay? All right, so I'll get started with what we can get started with.